Section 4.8, Video 1, Probability Trees and Binomial Experiment. In this video, we will cover the following objectives. Use probability trees to calculate probability of conjunctions, probabilities of disjunctions, and conditional probabilities. Let's begin with example 1. Create a probability tree for the experiment. One coin is flipped and then a single six-sided die is rolled, and then we'll calculate the following probabilities. Let's begin with our probability tree. I'm going to make my tree horizontally, although there are other ways that you could make your tree. Here's my starting point. When we start, we flip a coin, and I'm going to draw a branch for each of the possible results. There could be a heads, or there could be a tails when that coin is flipped. On the heads branch, the probability of getting a heads is 1/2, and the probability of getting a tails is also 1/2. Notice the total of that branch, of those branches, equals 1. The next part of the experiment continues with rolling a single six-sided die. When rolling a die, there are 6 possible options. So after the heads branch, I'm going to draw 6 branches, one for each possible result of rolling the die. A 1, a 2, a 3, a 4, a 5, and a 6. On each one of those branches, the probability is 1/6. And notice that the total of those branches also add up to 6/6 or 1. After the tails branch, I'm going to repeat that same idea that we have 6 possible branches, and each branch, 1 through 6, is going to have a probability of 1/6. Now, to finish my probability tree, I like to write the probability of the complete branch at the end. So following the very top branch, it would be heads and a 1, and that gives us 1/2 times 1/6 for the probability of the intersection of both of those, heads and a 1, is 1/12. Notice that they all have 1/2 times 1/6 in this particular probability tree. So each of the 12 branches is going to have a probability of 1/12 for this particular example. Now let's go ahead and begin with part A. Part A says find the probability of heads first and a 2 second. When they're listed in order with a comma, they are being given a very specific order. So following the heads branch first and the 2 branch second, we see a total of 1/12 for our probability. That is our answer. Part B is a little bit different. It says find the probability of a tails or a 3. Now in this case, because of the or, we're going to look at any branch, and I'm going to circle them in red, any branch that has a tails or any branch that has a 3, and using the inclusive version of the word or, it could have a tails or a 3 both. So we could start out with heads and 3 is 1/12. There's also tails and 1, tails 2, tails 3, tails 4, tails 5, and tails 6 as other branches that also meet the description. And notice that we would end up with 7 total branches, and each one has a probability of 1/12, or we end up with a total probability of 7/12. Okay? One thing to note is that as you move through consecutive branches, heads first and then 1 second, you're multiplying those probabilities, and when you're becoming more specific, heads first and then 1 second, that's an intersection of events, and you're multiplying the probabilities, and the probability becomes smaller as you become more specific. In part B, we were looking at more than one branch meeting the description, and so we took the total complete branch and we added any branch that met our description, and by adding the branches together, our probability increased and became more likely. Let's take a look at part C. Find the probability of rolling a 6 given that we know heads was flipped first. Now in this case, there's more than one way to calculate this. The first way I'm going to calculate it is using our conditional probability formula. And that says the probability of the intersection, a 6 was rolled and a heads was first, in the numerator, and in the denominator, it's the probability of the given, which that heads was first. So if we follow the branch for 6 and heads, that would be following heads first and 6 second, we get 1/12. Looking at the denominator, heads first is 1/2. This becomes 1/12 divided by 1/2, or using our arithmetic 1/12 times 2/1, and that ends up reducing to 1/6. Notice that we can get the same answer if we move our starting position. I'm going to use a yellow highlighter, and if we know that heads was flipped first, I'm going to follow to where heads was flipped first and highlight that in yellow. And that yellow dot over the heads first is my new starting point. From there, I can then follow to where a 6 was rolled. And notice that the probability on that branch is 1/6. So we're ignoring the 1/2 because it's no longer an if situation. We are given that heads was first. So starting at heads first, following the branch just to rolling a 6 is a probability of 1/6, and that's the same answer. Let's take a look at part D. Part D says find the probability that a tails was flipped if we are given the knowledge that a 1 was rolled. So we know a 1 was rolled, but keep in mind that when we look at our tree, we can't get to a 1 rolled first. The rolling of the dice happens second. So in this case, unlike moving to our heads first in part C, we're not able to do that shortcut. We're going to have to use our formula. And our formula says probability of the intersection, tails, and a 1 was rolled. And the denominator, probability of the given, which is that a 1 was rolled. In our numerator, tails and a 1 was rolled. I'm going to use green. I'm going to follow the tails branch and a 1, and I get the probability of 1/12. In the denominator, I want to include any branch that a 1 was rolled. So that would include a heads and a 1 for 1/12, or that would include tails and a 1 for 1/12. And adding that 1/12 and 1/12 together, we get 2/12. So I have 1/12 divided by 2/12. Simplifying, you're going to find that we end up with 1/2. Let's take a look at another example. Here's a quick note that when our events become more specific through the intersection, the overall probability typically decreases with each successive detail. That was like when we discussed the probability of heads first and a 1 second, that our probabilities were multiplied together and became smaller. The second note is when we had an event that had more than one way to meet the description, like probability of tails or a 3, then it's more likely to occur, and by adding those complete branches, our probability increases. Probability trees with replacement. Example 2. Create a probability tree for the following experiment and then find the following probabilities. A bag of marbles contains 5 blue and 3 white marbles. Let's begin by creating a probability tree for the experiment of choosing 3 marbles with replacement, meaning you'll choose the marble out of the bag, look at what the marble color is, and then place the marble back into the bag. Here's our starting position, and when we reach in for the first marble, we have 2 choices. It could be a blue marble or it could be a white marble. So we're going to have one branch representing the blue marble that could come out and one branch representing the white marble that could come out. Putting the probability of blue on the blue branch, there are 5 blue marbles and 3 white marbles for a total of 8 marbles. And 5 of them are blue, so the probability of blue is 5/8. On the white branch, the probability of white is 3/8. Reaching into the bag for the second marble, we could have 2 options, blue or white. And again, because we replaced the marble back in the bag, there are still 8 marbles in the bag, and 5 out of the 8 for a probability of 5/8 blue, and 3 out of the 8 for a probability of 3/8 are white. Looking at the bottom branch for white, if white was selected first, again, when we reach into the bag a second time, we have 2 options, blue or white. And again, the probability of blue remains 5/8 and the probability of white remains 3/8. Reaching into a bag the third time, we still have those same 2 options, blue and white. I'm going to go ahead and write the blue and white branches from the end of each of the 4 branches we had after the second choice of marble. And remember, because we are replacing the marble back in the bag, we still have 8 marbles, and on each one of these, the probability of blue is 5/8, and the probability of white is 3/8. Notice that that set of blue and white totals 8/8. And each time for blue, we're going to have a probability of 5/8, and each time for white, we're going to have a probability of 3/8. We can complete our tree diagram by finding the probability at the end of each of these branches using our probability of intersection to multiply the individual probabilities together. Looking at the top branch, blue, blue, blue would be 5/8 times 5/8 times 5/8, which ends up giving 125 out of 512ths. The second branch down was blue, blue, white, or 5/8 times 5/8 times 3/8, for a total of 75 out of 512. The third branch was 5/8 times 3/8 times 5/8, for a total of 75 out of 512. The fourth branch, 5/8 times 3/8 times 3/8, gives a total of 45 out of 512. The fifth branch, 3/8 times 5/8 times 5/8, representing white, blue, blue, would give us a total of 75 out of 512. The sixth branch, 3/8 times 5/8 times 3/8, is 45 out of 512. The seventh branch, we have white, white, blue, or 3/8 times 3/8 times 5/8, for another total of 45 out of 512. And the very bottom eighth branch represents white, 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 or 3/8 times 3/8 times 3/8, which gives a total of 27 out of 512. If you add these totals at the end, you should find that you get 512 out of 512, and that set of branches totals 1. Part A, we're looking at the probability of 2 blue marbles. Notice that they are mentioning exactly 2 blue marbles, not at least 2 blue marbles. I'm going to highlight the branches where we have 2 blue marbles. That would be blue, blue, white, for a total of 75 out of 512. Blue, white, blue also gives us a total of 75 out of 512. And then we have white, blue, blue, which gives us a total of 75 out of 512. Putting those probabilities together, because more than one branch meets our description, we have 75 out of 512 plus 75 out of 512 plus a third 75 out of 512, giving a total of 225 out of 512 for the probability of selecting 2 blue marbles. Part B, find the probability of selecting at least 1 white marble. If we have at least 1 white marble, I'll highlight these in green. That would be blue, blue, white, for a total of 75 out of 512. Blue, white, blue, 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 white, white, blue, blue, white, white, blue, white, blue, white, and also white, white, white at the very bottom branch. If we add the sum of those, that would be 75 out of 512, plus another 75 out of 512, 45 out of 512, 75 out of 512, plus 45 out of 512, plus 45 out of 512, and that bottom branch of 27 out of 512. Adding them all together, we get a total of 387 out of 512 for the probability of at least one white. There is an alternate way to calculate part B. If you notice, all of the green circles that we had for probability of at least one white in the branches that we combined together, it included every branch except the very top branch of having all blue marbles. So we could use the complement here. And the complement would be probability of at least one white marble is the same as 1 minus the probability of not at least one white marble, which is 1 minus the probability that they're all blue. Because if you don't have at least one white, then they were all blue. Probability of all blue was that top branch, which was 125 out of 512. Finding common denominators, we get 512 out of 512 minus 125 out of 512 to give us that same total of 387 out of 512. Notice the same answer, but two different approaches. And that ends example 2.